Okay, so what are your morning coffee, that spicy kick in your favorite food, and even life-saving medicines all have in common? I know, it sounds like a riddle, right? But believe it or not, there is a fascinating hidden connection between them all. And it's a connection that shapes, well, pretty much everything in our world.
Let's start with something familiar. That morning boost you get from your coffee? Well, that's thanks to a specific little molecule called caffeine. It's a natural stimulant, and for a lot of us, it's what gets the day started.
Okay, how about the heat in your food? You know, that kick you get from a good hot sauce? That comes from another compound. This one's called capsaicin. It is the one molecule that gives chili peppers that signature fiery spice.
And then you've got life-saving medicines. And I mean the whole range. We're talking everything from the antibiotics that fight off infections to the plastic syringes that deliver the medicine, even things like synthetic heart valves. Yep, they all belong to this same mysterious group.
So, what is it? What's the secret ingredient? What's the one thing that ties all of these incredibly different things together?
Well, that hidden connection is actually a field of science that's happening all around you and inside you every single moment of every day. The answer, it turns out, is in a very specific branch of chemistry. And here we have it, organic chemistry. Put simply, it's the study of any compound that has the element carbon in it. That's the link. Caffeine, capsaicin, plastics, medicines, they're all built from molecules that have a carbon backbone. It's all about carbon. So, why carbon? I mean, what makes this one element so special that it gets its very own dedicated branch of chemistry? Well, it all comes down to a few really simple but incredibly powerful rules that let it build the molecules of life itself. And believe me, this is no exaggeration. Just think about it. The natural fibers in your clothes, like cotton and wool, the synthetic ones, like nylon, the food we eat, the fuels we burn. Organic chemicals are literally everywhere. All right, let's get into the details, because this is where we find carbon's real superpower. It all comes down to a few really simple, elegant rules that let it create an almost infinite variety of amazing structures. And the most important rule of all can be boiled down to a single number: 4. That's it. Carbon always wants to form 4 stable connections, what chemists call bonds, with other atoms. Remember that number: 4. It's the key to everything. And here's a perfect example of that rule in action. This is a molecule of methane. It's the main stuff in natural gas. See that carbon atom right in the middle? Count the lines coming off of it. 1, 2, 3, 4. 4 bonds. And now look at each of the hydrogen atoms. They each have just 1 bond. 4 for carbon, 1 for hydrogen. See? It's that simple and that consistent. But here's where things get really interesting. Carbon isn't just great at bonding with other elements, it's amazing at bonding with itself. It can link up with other carbon atoms, which lets it form the backbone for huge, complex molecules. And this is where you can really see carbon's versatility. Take a look. It can connect to another carbon with a single bond, like a simple handshake. But it can also form a double bond, 2 connections, which is stronger and changes the shape. It can even form a triple bond, and each type of bond totally changes the molecule's properties. This flexibility also means carbon can build structures in different ways. It can form long chains, kind of like a string of beads, or it can loop back on itself to form super stable rings. These 2 shapes, chains and rings, are basically the fundamental Lego bricks for millions and millions of different organic compounds. Okay, so we've got our star element, carbon, but it rarely works alone. It loves to bring other elements into the mix to create even more variety and function. Now, in the world of organic chemistry, there's a special name for any atom that isn't carbon or hydrogen. It's called a heteroatom. The best way to think of them is like special guest stars. They show up and bring all sorts of new and exciting properties to the molecule. The most common guest stars: oxygen and nitrogen. And guess what? These guest stars also follow simple, predictable rules. Just like carbon always makes 4 bonds, these guys have their own numbers. So hydrogen, as we saw, always makes 1 bond. Oxygen almost always makes 2. Nitrogen usually makes 3. And of course, our star carbon is always 4. It really is like a simple, predictable construction. So just to lock that in, our toolkit has some simple rules. Oxygen makes 2 bonds, nitrogen makes 3, and other elements like the halogens, think fluorine and chlorine, they just make 1. Remembering these simple numbers is the key to understanding all of this.
Okay, let's see what this looks like in practice. On the left, we've got our old friend methane, just carbon and hydrogen. Now, watch what happens when we just swap out one of those hydrogens and pop in an oxygen group instead. Boom. We get methanol, which is an alcohol. Just by adding one little guest star, that one heteroatom, we've totally changed the molecule's identity and what it does. And with that, we can finally come full circle. Let's go back to that capsaicin molecule, the one that makes pepper spicy. We can actually look at this complex thing now and understand it. You can see the long carbon chain, you can see the carbon ring, and if you look close, you can spot the guest stars. There are the oxygen atoms, and there's the nitrogen atom, all perfectly following their simple bonding rules.
And that really is the beautiful secret of organic chemistry. From just a handful of elements and a few surprisingly simple, predictable rules, you get this incredible, almost infinite complexity, the kind of complexity that creates flavors, medicines, plastics, and even life itself. And it really makes you wonder, doesn't it? What other simple hidden rules are out there just waiting for us to discover them?